In this video, I'm going to explain you about the internal direct sum. Okay, so I'll take a vector space V and I collect some subspace of V. So I'm taking the subspace of V as U1, U2 till Un. Okay, be the subspace of V. Then this V can be written as the summation of this. Okay, so U1 plus I means internal direct sum. Okay, U2 plus I internal direct sum, U3, so on till plus I Un. If for every V means I take any V belongs to V. Okay, then there exists unique UI from each. Okay, there exists unique UI belongs to UI for 1 is less than equal to I is less than equal to N, such that this V can be written uniquely as the elements of this. V can be written as U1 plus U2 till UN. Okay, and remember, if I take any subspace from here and I intersect, okay, if I take any subspace from here and I intersect with the summation of this other subspace, excluding that subspace, I should get only 0 element. Okay, I should get only 0 element for all 1 is less than equal to R is less than equal to N. Okay, so this is the definition of the internal direct sum. So I have given one remark. This is in a term. So suppose we take two subspace. Okay, suppose I take U and W are two subspace of V. Then V is called the internal direct sum of U and V, and we write as this. Okay, we write as this. If I take any element here, it can be uniquely written. Okay, it can be uniquely written as U plus W. Okay, so that is also I'm going to explain here. So we have V equal to U plus W. But you should be very careful. You have to remember that the intersection between these two subspace should consist of only 0 element. Okay, the intersection of these two subspace should be only 0 element. Then only we can write as the internal direct sum. Any vector space can be written as the sum of two subspace as the internal direct sum if the intersection between the two subspace should be consisting of only 0 element. It should not consist of any other element. Okay, and if I take any element here, there exists unique element U belongs to U and W belongs to W, such that V can be written as U plus W. Okay, that V can be written as U plus W. This is also called the internal direct sum of two subspace. Okay, so in this way we can define the internal direct sum. Now we are going to do one theorem here, that if V be an internal direct sum, so we are taking an internal direct sum of U1, U2 till Un, then this V is isomorphic to the external direct sum. Okay, if U1 is an internal direct sum, if V is the internal direct sum, then this is isomorphic to the external direct sum. Okay, so this is a isomorphic. So let us define a mapping from V to this. These are the external direct sum. Okay, these are the external direct sum of here. So this is U1, this is U1, this is U2, this is your UN. Okay, so these are U1, U2 till UN. Now I'm defining a mapping. I take one element in this. So this is the internal direct sum. So every element here can be written as the linear combination of all the elements of this form, where U1 belongs to subspace U1, U2 belongs to the subspace U2, and so on. Okay, in a unique way. Now we are defining how phi of V means this element is sent to the external direct sum. So this will be sent to coordinate wise. So we have U1, comma U2, so on till UN. Now we have to check that this is well defined. So I take two element in here. Okay, in V I'm taking two element. So and if I take two elements, the element will look of this type. Okay, will be of this type. So I'm taking this. So this is of this type in addition form, because these are the internal direct sum. So it will be looking of this type. And I take these two are equal. Then I have to show that U1 is equal to U1 dash. Okay, so I have to show that. So I take these two are equal. So we have this. Okay, we have this. So we have this is equal to this. Okay, now these two are equal. So that means this U1 is equal to U1 dash. So UI is equal to UI dash. for all I. Okay, where I is equal to 1 to n. So we have shown that phi is well defined. Okay, we have shown already phi is well defined. It's clear with this. So we have shown that phi is well defined. Now next is that we want to show phi is a vector space homomorphism. So I'll take two elements from V. So the element looks like this, and I take one scalar from the field. Okay, so I'm taking one scalar from the field. So phi of V plus V bar. So we have V is this, V bar is this, but it is commutative. It is abelian group under addition, so we can interchange. So we have U1 plus U1 dash, U2 plus U2 dash, and so on till UN plus UN dash. So applying the definition of phi, this can be written coordinate wise as this. Then we can separate into two coordinates, so we get this. So this is phi of V plus phi of V dash. That is one property of the vector space homomorphism. And let us check the second property. So we have phi of alpha V. So we have phi alpha V is of this type. You multiply alpha to this. So this, since using the definition of phi, we can write as coordinate wise. So we get alpha U1, comma alpha U2, so on till alpha UN. You can take alpha common, so we get U1, U2 till UN. Okay, so this is f of phi of V. So we have shown that it satisfies both the condition of the vector space homomorphism, hence phi is a vector space homomorphism. Next we'll try to show it is 1, 1. I take two elements whose image are same. So we have this, V is of this type, and this, if I apply the definition, it will be coordinate wise in this form. It will be coordinate wise, okay, this form. So this, okay, this is of coordinate wise. Now this coordinate, this is equal to this, means we have two coordinates which is equal. That means only if this is possible, only if the first coordinate is equal to the first, second is equal to the second, and so on. So we have here ui equal to ui dash for all I equal to 1 to n. So that shows that these two are same. V is equal to V dash, hence phi is 1, 1. We have shown phi is also 1, 1. Now our aim is to show that phi is onto. So I take an element in the external, I took an element in the internal direct sum. Sorry, I took an element in the external direct sum. So this is E, this is also E, and this is E. I am taking in the domain. So this is the external direct sum. So I'm taking an element in the external direct sum. So the element will be coordinate wise, okay, where ui belongs to ui for all I. Okay, so I take one element in V, then V can be written as, these are the internal direct sum, so we can written as a linear combination of this. So phi of V is phi of this, so phi of this is equal to this, which is equal to x. So that shows that phi is onto. Hence phi is an isomorphic, okay, hence phi is an isomorphism. So we have shown that the internal direct sum is isomorphic to an external direct sum. Thank you.